So we're going to continue on with section 14.3, Intermolecular Forces. We talked about dipole-dipole forces, and now we're going to talk about London Dispersion Forces. These guys go by several different names. The name I prefer is induced dipoles. And now we're going to all stop and stare at the people that are talking. It works so well. That's what I love about teaching college. It doesn't work with my kids. Okay. So these London dispersion forces or induced dipoles happen kind of accidentally or spontaneously. So here we have an illustration of an atom, and the electrons are on the outside of the atom, and the protons and neutrons are in the nucleus. So there's a positive charge in the middle, and then the electrons are out here. And we didn't talk really a lot about what those electrons are doing, but they're just kind of, let's just think of them as being in a cloud, kind of random. They're actually extremely random. So they're out there. Well, it can happen that they can get kind of lopsided. They can just all be over here on one side, just randomly. So a little bit like my kids, I think this has only happened once, and I actually did manage to get a picture of it. All 6 of them happened to be sitting on the couch at once for no prearranged reason. It wasn't like they were, waiting for something or anything. I came in there and there were all 6 of them on the couch, and I'm like, wow. So usually they're kind of spread around the house and they move about, and it's kind of, equally distributed, but occasionally they're all bunched up together, and that can happen with electrons in atoms as well. Well, what happens when all the electrons, or more of the electrons, are on one side? Well, that side of the atom becomes partially negative, and the other side of the atom becomes partially positive. Well, this can have an effect on a neighboring atom. So this positive side here attracts the electrons in the neighboring atom and causes them to move over, and this also becomes imbalanced. Gets an instantaneous dipole. This is an induced dipole now, because it was induced by the randomness of this guy. But we have this force of attraction between positive and negative. And then these guys go back to being, I lost my arrow. These guys go back to being random, and those guys go back to being random, and it's over. So London dispersion forces are induced dipoles that happen just spontaneously, and they're very brief, but they happen over and over again. So even a tiny force, if it happens many times, can be significant. London dispersion forces are more significant in large atoms or molecules because that electron cloud is larger and more diffuse and is more easily swayed to be lopsided. These London dispersion forces happen in all molecules. So they happen in nonpolar molecules and polar molecules, and they also happen in atoms. So all substances have London dispersion forces.
So in this, it goes there and then it goes back? So
yes.
So what's the significance of that? Like what happens? Or what's the benefit?
What's the significance? Okay, so we get an imbalance here, just spontaneously. Another analogy is to think about if you go up to San Francisco and go to Fisherman's Wharf, you can take a blue and white cruise around the San Francisco Bay. And so a whole bunch of people get on a boat. And you're all up on deck so you can see, because that's why you went on the cruise, is to look around. So, people are kind of spread out around the boat. Well, sometimes it could happen that everybody just sort of happens to be on one side of the boat. Maybe not everybody, but most of the people go to one side of the boat. And then the boat may list a little bit. Hopefully, they didn't overload it and it's not going to tip over, right? That would be bad. But the boat might list a little bit. So that's like this induced dipole here. All the people went to this side of the boat, and now the boat's a little crooked. And this positive charge here attracts the electrons here. So that's like the boat going around Alcatraz. It's going around Alcatraz. If you're on the wrong side of the boat, you can't see Alcatraz. One of the reasons you went on this cruise was to see Alcatraz, right? Everybody goes to that side. So Alcatraz is inducing an imbalance on the boat. Does that make sense? So this one, just spontaneously being lopsided, induces the neighboring atom to be spontaneously lopsided. And that can induce the next one, and the next one, and the next one. And so when you have both of these imbalanced at the same time, you have an electrostatic attraction between this positive and negative. It's very similar to what we had with the dipole-dipole forces. Okay, sitting just doesn't work. It's similar to what we had with the dipole-dipole forces, except that it's not constant. With polar molecules, you have a permanent dipole. There's always a positive, negative end, and so there's always that attraction. These attractions come and go, and they're smaller than the permanent dipole forces. Does that make sense?
What's kicking them back out?
Well, these guys, the electrons are always moving, and here they just happen to be lopsided, and there's really no benefit for them to stay that way. So they're going to just go on their random way and go back to being spread out again. The induced dipole...
The induced one.
Well, the original one, the induced dipole is not enough to cause that dipole to remain forever. Or even to, it'll induce a dipole in the neighboring one, but it doesn't last very long. So my kids all sat on the couch together for a few minutes, but then they got up and they went their own ways again. And it doesn't, you just can't keep them all sitting on the couch for more than like 2 minutes. It's not going to work. Because electrons are squirrely like little 4-year-olds.
But the original atom maintains that imbalance?
No, the original atom does not maintain its imbalance. So the imbalance happens spontaneously. It induces an imbalance in the neighboring atom. There's this brief attraction, and then the original imbalance goes away. And then the induced imbalance goes away also. So this is a very brief attraction that comes and goes. Does that satisfy? Okay. So it is more significant in larger atoms, but it doesn't occur in all atoms and molecules. And here's another picture. So here we have a hydrogen molecule. So each hydrogen has an equal attraction for the electrons, and this bond is going to be a covalent bond, and it's nonpolar. But we can have the electrons be over here. See, in a hydrogen molecule, each hydrogen has one electron, and so there's only 2 electrons here. And if they both happen to be over on this end, then this end's going to be a little bit positive, that's a little bit negative, and that induces a dipole in the second molecule. That's why I like the term induced dipole forces, because it's more descriptive. London was the name of the guy who described this, so I don't know why dispersion forces. But these London dispersion forces are really the only forces of attraction, the only intermolecular forces for nonpolar molecules or for atoms. Atoms cannot be polar because it's just a single atom. These London dispersion... Well, yeah, because a molecule can be imbalanced because if you have 2 atoms like hydrogen and fluorine is more electronegative. It has more attraction for the electrons. And so that's a polar molecule, and it's always going to be imbalanced. It's kind of like between a perfectly covalent molecule and an ionic compound. It's sort of in the middle. When you have an atom, you've got the nucleus and you've got the electrons around it. And there's no reason for that electron cloud to be permanently skewed or out of balance. It can temporarily become that way, but generally it's going to be more balanced.
Which is an ion.
An ion will always have either a positive or a negative charge because it's missing an electron or it has an extra electron. But atoms have the same number of electrons as protons, and so overall they have no charge. So we can look at the freezing points of these different noble gases and see how the size of the atom affects the strength of the intermolecular forces. So these are all elements, monatomic elements: helium, neon, argon, krypton, and xenon. They're noble gases. And as we go down, these are in the order in the periodic table. Xenon has a molar mass of 131, and helium has a molar mass of 4. And we can use molar mass as kind of a gauge of how big a molecule is, or an atom. So xenon is larger. Xenon has a higher freezing point than helium does. Helium, actually, the only way you can get it to freeze is it's 1 degree above absolute zero, and you can only get it to freeze if you put 25 atmospheres of pressure on it, which is 25 times normal atmospheric pressure. That's a lot of pressure. It boils at it boils at 4 Kelvin, which would be minus 269 Celsius. And so it's almost impossible to get it to freeze. But if it did freeze, it would be minus 272. Neon, minus 248, and these go up. So xenon freezes at minus 111. So if you take the solid, it's easier to think of the melting point. I don't know why they do freezing. I think it's easier to think of the melting. So if you take solid xenon and you add energy to it until the movement of the atoms is enough to break loose from those intermolecular forces that are holding it together. That's going to happen at a higher temperature for xenon than it is for, say, neon, because the forces of attraction are stronger. The dispersion forces for neon are stronger than they are for krypton. Krypton's stronger than argon, argon's stronger than neon, neon's stronger than helium. Helium's dispersion forces are incredibly weak, just almost non-existent. Does that table make any sense? We can look at the melting point or the boiling point of a substance and use that to gauge the relative strength of the intermolecular forces. Higher melting point, higher boiling point means stronger intermolecular forces. Oh, there we go. In general, stronger intermolecular forces, the higher the melting and boiling points.
So it's the intermolecular forces that change when it's changing states.
Yeah, the intermolecular forces are overcome when state changes occur. So in a solid where the particles are fixed relative to each other, the atoms or molecules are held in place by the intermolecular forces. When that melts, those particles have enough energy that they can break some of them. But as they break one, they form a new one. And so they're moving around, but they're still held close together. When it goes into the gas state, it can break completely free of all the intermolecular forces. So it's a little bit like, people wearing Velcro suits or something, and, you're like stuck. And it's like, okay, I have to move. I have to move kind of fast to get unstuck from the person next to me. But then as I move away from them, I'm bumping into other people and I'm sticking to them. And so you have to keep exerting energy to unstick from the people. I know, that's weird, huh? I need to come up with something better. Sticky tape, maybe. I don't know. If the clothing is not sticky, if it's slippery, maybe we're all wearing Teflon suits and you just slide. You don't stick at all, right? The weirder it is, the better it is. That's like low intermolecular forces. And you can move relative to the person next to you with very little effort. because there's nothing that's sticking you to them.
See, I understand that part. I don't understand why it's warped. Because if they're all moving, right, randomly, right? How is that what it's attracted to? Is just by another one passing by it?
Right.
And that breaks the force and then attracts it to that.
Yeah, so in a liquid, you have the forces of attraction are all there, but the liquid's moving fast, and the particles are moving fast enough that they can break them. But as they break that one, they run into another one and get stuck to that. Then they have to break that, but then they run into another one. And so those little, like it's a lot like magnetic attractions, but it's electrostatic. So it's, you're breaking the attraction with this one, but then you're forming one with that one. And then you have to break that one, and then you form with the next one. But you're able to move. In a solid, you are attracted so strongly, or really you don't have the energy of motion to be able to break free at all from the ones next to you. And so you're just kind of stuck there. And then in the gas, they have enough energy to just break loose from all of them and go zinging off into space. And now they're moving so fast that when they do bump into that random molecule, they just bounce off.
So that was my next question. So at some point, some of them obviously are going to be going so fast that they're just gone out of the group, and that's when it changes state.
Yeah, from a liquid to a gas. When it melts, you're just losing. You're moving from that grid, and but you're still stuck in that general area because you're still touching other molecules, and they're still kind of grabbing onto you. So, which molecule is capable of forming stronger intermolecular forces? N2 or H2O? H2O. Why? H2O, because H2O is polar, right? So it has dipole-dipole forces. And it's got a hydrogen-oxygen bond. So it has hydrogen bonding. And it has London forces, because all molecules have London forces. N2 is nonpolar. It's nitrogen bonded to nitrogen. They have equal attraction for the electrons in that bond. It's a nonpolar molecule. So nonpolar molecule only has those London dispersion forces. The London forces are the weakest forces. Dipole-dipole forces are the next stronger, and the hydrogen bonding is the strongest. And so water has the stronger intermolecular forces compared to nitrogen.
What's the order again?
London forces, dipole-dipole forces, hydrogen bonds. Hydrogen bonds are the strongest. And the dispersion forces are the weakest, the London dispersion forces. Because those London dispersion forces come and go. They're not always there. The dipole-dipole forces, that force of attraction is always there. And then the hydrogen bond is just an extra strong dipole-dipole force. So since the water has stronger intermolecular forces, would you predict that its boiling point is higher or lower than nitrogen? Higher. Okay, because if the boiling point is higher, what that means is the particles have to have more kinetic energy, more thermal energy before they can break free. So higher melting and boiling point correlates with stronger intermolecular forces. I saved you the step of drawing the two Lewis structures. So here's a formula, C2H6O. We can actually draw two different Lewis structures for these. And let's compare the boiling points. Which do we think would have a higher boiling point? the one on the left. Why? It's going to be polar, and we've got hydrogen-oxygen bond. So this guy could have hydrogen bonding, right? This one looks much more symmetrical. It is actually polar. This atom in the middle has some lone pairs, and so this guy is bent, and this does have some polarity to it. But can this do hydrogen bonding? No. The oxygen is bonded to carbon. Carbon-hydrogen bonds don't qualify. So it has to be ET phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. So
What's the question again?
compare the boiling points.
And
So-
isn't the carbon bond pretty strong too? Carbon to carbon?
Well, it's a strong bond, but we're not concerned with the strength of the bond because we're not breaking bonds. We're talking about strength of intermolecular forces.
Because the
And so
bonds don't change.
the bonds don't change. So this has a lower boiling point because it has weaker intermolecular forces. This means that we can have hydrogen bonding.
Even though you have hydrogen in the other one, you
Right.
don't have bonding.
Right. It's not enough to just have hydrogen and oxygen in the molecule. The hydrogen has to be bonded to oxygen, nitrogen, or fluorine in order for there to be hydrogen bonding.
What would make it bond whichever way? Could it bond either way?
Well,
Or would it bond a certain way?
it depends on how those molecules were formed. So this is ethanol, and this is dimethyl ether. And these are two different organic compounds, but they're called structural isomers because they have the same number of carbons and hydrogens. They have the same formula. They're just combined in different ways. Yeah. And it's not going to go back and forth between them. It's not going to change around. These covalent bonds are going to remain unless it undergoes a chemical reaction. And we're not talking about chemical reactions right now. We're talking about state changes. We're talking about breaking the intermolecular forces, not the intramolecular forces. The bonds remain, and a hydrogen bond, even though it has bond in its name, is not really a bond. It's just an intermolecular force.
So you can have the same formula, different structure.
Yes. And this is especially true in organic molecules. And the larger the molecule, the more possible isomers there are. And so you can have the same formula, and you might have 20 different compounds. And they're going to have different properties and react differently. Some of them are going to explode. This one is dimethyl ether, which would be a gas at room temperature. And this is ethanol, or ethyl alcohol, which is what's in vodka and whiskey and beer, and that's a liquid at room temperature. This has a higher boiling point because it's got hydrogen bonding, and so it's got stronger intermolecular forces that hold it together more. You guys ask really good questions.
Is that good?
It is good. Yes, questions are good. I'm going to skip that one. Consider the following compounds. How many of these compounds exhibit London dispersion forces? All of them, yes! It's like a kind of a trick question. So letter D, 3. All of them do. All substances have London dispersion forces. There we go. That's what we were supposed to finish on Wednesday.
Okay, so